Hi everyone. In today's video, we're going to code neighbor sampler using JAX for graph neural networks. In my last video, I talked about sampling methods for graph neural networks, but for all of these methods, I used pytorch-geometric. So I wondered, how does it look like in JAX? So the most used sampler for graph neural networks is the neighbor sampler that was introduced in GraphSAGE paper. So I tried to code it here in JAX because, as far as I know, jraph library doesn't have samplers. It has only the GNN layers and graph attention layers and the data structure for graphs, but it doesn't have samplers, just like pytorch-geometric and DGL. So in this video, we're going to code neighbor sampler using JAX, natively in JAX, and then we are trying to test the GNN using full batch training and mini batch training using our neighbor sampler. So let's get started. I have to admit that my implementation is not that efficient. And if you come to me and say, Mashan, I don't trust your code, I would say, fair enough. Then you say, but what are my options? I want to train my graph neural networks in JAX using mini batch training. So I would say that your options is just to use the samplers from pytorch-geometric library or from deep graph library, DGL. And instead, these samplers will produce torch tensors. So you have to convert everything into jax.numpy. Then you have to run and load these jax.numpy arrays into data loaders and just to train your neural net in JAX. So before I start, let's review some undergraduate stuff. You probably remember from your undergraduate course that a graph can be represented. So this is a graph, node number 1 connected to with two edges to number 2 and node number 3. So you probably remember from your data structure course that a graph can be represented using a adjacency matrix, where the nodes are stacked along the row dimension and the column dimension. It's a squared matrix, and we got one wherever there is an edge. So there is an edge between 1 and 2. So this is represented by this matrix entry, and if it's undirected graph, we would have a symmetric adjacency matrix, and if it's a directed graph, we would have asymmetric adjacency matrix. You remember that also there is another representation other than the adjacency matrix, which is the edges list. So in the edges list, we would have on the first column we would have the source nodes, and on the second column we would have the destination nodes. And sometimes we have to add another column for the weight on the edge. But if the weights are always 1, zeros and ones, we could discard that column, because we assume that if an edge is present in the edge list, then it would have a weight equals 1. But in practice, and all of the graph methods and libraries, they don't use the adjacency matrix. Because if you use the adjacency matrix, then you have to reserve in memory n by n space. It's very efficient to store a graph in edges list. Sometimes they call it a sparse representation. And this introduces a new kind of arrays in machine learning libraries called sparse matrices. So what is a sparse matrix? One of the most used methods for sparse matrices is the scipy sparse. Is the scipy.sparse.csr array. So the concept of a star matrix, it's just like the concept of edges list. So this is the row 0, 0, 1, 2, 2, 2. These are the source nodes. And this is the column. These are the destination nodes, which is 0, 2, 2, 0, 1, 2. And this is the data, the weights and edges. If we put everything into a csr.array, then convert it to array, it will gives us the dense representation, the squared adjacency matrix. You would notice that between 0 and 0, this is a self loop. An edge with weight 1. Between 0 and 2, an edge with weight 2. Between 1 and 2, an edge with weight 3, and so on. So this is how sparse matrices work. They work on a 3-column matrix, and the number of rows equals the number of edges in your graph. It's very efficient to store a graph in an edge list. When I got to know the sparse matrices, for me it was mind-blowing. You remember in your undergraduate when you start programming, first you would First, you would use print statements to print hello world or print your name. And in my case, it was Java, so it was system.out.println, and we used to print our names for 3 times, 5 times. Then in the next week, they introduced us to the concept of for loops, and it was mind-blowing at the time. So what we said to our lecturer, are you kidding me? Can I do that with a single line of code? So I don't have to copy all the print statements. I just have to run a for loop. For me, it was the same when I was first introduced to sparse matrices, because I couldn't. There are so many things that I could do with sparse matrices. I'll give you one use case on how to use sparse matrices. So in my PhD, I used to do spectral clustering, and first I used to do this. For all I and I's and for all J and J's, I have to compute this formula. So this formula actually computes the weights on edges between the nodes on the graph. Just to explain this formula, because I hate showing any math formula without explaining them in plain English. And so this is what does it mean, this formula. xi minus xj, how far is xj from xi? For example, they are 6 apart. The square here, I don't care if they are plus 6 apart or minus 6 apart. They are 36 away from each other. So I'm taking the absolute value of the difference. The minus here, the closer the distance, the better. I want to assign more weights on the closer neighbors, because I prefer having closer neighbors. The sigma in the denominator represent the are we including farther neighbors. And this whole quantity will be plugged into an exponential function just to retain a scale value between 0 and 1. So this is what this formula represents in plain English. And I want to just show you a reference that should be your go-to reference when it comes to computing the pairwise similarity in spectral clustering or any dimensionality reduction algorithm. So this paper is called Dimensionality Reduction of Multimodal Labeled Data by Local Fisher Discriminant Analysis by Masashi Sugiyama. So if you jump into Appendix D in this paper, so this appendix here, definitions of affinity matrix. The first one is the heat kernel. The heat kernel is just the formula I just showed you. So he also wrote about Euclidean neighbor, the nearest neighbor, and the local scaling. The local scaling, you have it's the same formula as the heat kernel, but you have a sigma I and sigma j. So you have basically, instead of having one unified sigma for all the points, you just adjust it locally. And yes, this is I strongly recommend going through this paper, because it explains how to compute the similarity between points. And this what I'm trying to say, that any formula in machine learning or deep learning should be explained in plain English, and you should ask, what does it mean in plain English? Because every formula has a meaning. So why do we use softmax before computing the loss? Because the logits are produced by the neural net. They're not scaled. We scale them using softmax, and we give higher probability to the maximum output. This will help computing the loss. So, and another question, why are we using ReLU function between layers in deep learning? Because deep learning is, because if we stacked layers and we multiply the input by the weights and we add the bias, this is a linear function. And a combination of linear functions would produce a linear function. So we have to include some non-linearity along the way. So every formula should be explained in plain English. This is what I'm because if we can't just explain the formulas in plain English, we won't have junior researchers joining the research community. I got carried away here, so let's get back to sparse matrices. I was trying to compute this nested for loop, and I have to do it for all the points in the dataset. But when I first introduced to sparse matrices, this was mind-blowing for me. So this is xi. Usually it's n-dimensional point, but for simplicity, I'm just putting here as one-dimensional point. In one column, I would compute the differences. In another column, I would compute the squared of the differences, and I just multiplied by -1. Then I would divide by sigma squared. Then I would just plug in that quantity into an exponential function. Notice that I'm not using any for loop for this process. I'm just working on a one-dimensional column vectors, and this was very efficient because you don't have to compute it for pair points. You just compute the same formula simultaneously for all the edges in your graph, and you just work on column vectors. So let's jump into the code. I want to acknowledge the help of JAX team for providing this tutorial on graphneuralnetwork, and I also brought some code from pytorch-geometric tutorials. So this is the reference for jraph library, and this is the reference for pytorch-geometric library. Here I'm installing the pytorch-geometric, and here I'm installing jraph. You'll probably notice that I got some errors here, but that's because I originally run this code on Google Colab, but now I'm showing it locally on my machine using VS Code, because I like how VS Code is shown Jupyter notebooks. So that's why I didn't install these libraries on my machine. So I'm setting here the random seeds. Then I'm creating a toy graph. So this is the edges. I'm using JAX.random integer generator using the random key I initialized here using JAX.random.prng key. So I'm asking for 50 edges with source and destination for numbers between 0 and 10. Then I'm concatenating the reverse of that edge. I'm trying to make the graph undirected graph. And also I'm randomly creating the features for the 10 nodes in two-dimensional space. Now I'm storing the edges into a sparse matrix. I'm setting the weights on the edges to be 1, and the rows are the source nodes, and the columns are the destination nodes. And the full size of the adjacency matrix is just 10 by 10. I'm creating a graph using a function called FromSide by sparse array, and I'm passing A, and I'm creating a directed graph. The node positions will be the features in two-dimensional space, and I'm plotting the figure. Here I'm drawing the nodes for the graph, and I'm drawing the edges. I'm setting the edges color to gray. This is the toy graph that I'll be working on just to show how the neighbor sampler works. So to understand the neighbor sampler, so what I'm trying to do here, so this is the GraphSAGE paper. This is the original graph. I'm trying to pick seed nodes. Then from these seed nodes, I will jump for one hop. Then from their neighbors, I'm jumping to their neighbors' neighbors. So I'm trying to jump for 2 hops. I'm not trying to jump for more than 2 hops. So this is the assumption I made in the code. So for seed nodes, I need some batching, because I will pass the seed nodes to the neighbor sampler, and I need this neighbor sampler just to create batches of seed nodes. So I borrowed this function from Stack Overflow answer. It will give me chunks, and I think this was there is a function to do that. So what does it do? I'm passing this list from 0 to 9, and I'm specifying 3. I want a batch size of 3. I'm passing a shuffled version of this list, and it's supposed to return 3 lists. This is the first one, and this is the second one, and this is the third one. Each one of these lists will present the seed nodes that I'm trying to create the subgraph from. So this function takes a list and a number just to cut the list elements into this number, and it will return a list of lists, and each list has the size n. So it creates batches from that list. This is natively, I think Python has natively introduced some function. Let's go Python. I think it's called iter. Yeah, here it is. So here, this function, batched. So if you pass this list, roses, red, violets, blue, sugar, sweet, and you pass it to batched with the batch size equals 2, it will cut it into tuples. Roses red in one tuple, violets blue in another tuple, and in the last tuple has a sugar sweet. And this is if you batch A, B, C, D, E, F, G into 3, this is what will happen. And the last batch just return, if it's smaller than n, it will just return whatever is remaining in the list. But I could not run this in Google Colab because this was introduced in Python 3.12, and the Google Colab version I have is 3.10. I just tried to upgrade the Python Colab into 3.12, and then I run into all kinds of problems. Then I just stopped that solution and use this function here. But if you have the Python 12, just use the iter tools .batched. So this is the list that will create the seed nodes, and from these seed nodes, I will just start sampling edges from the graph. So for example, if you remember this graph here, 1 is connected to 2 and 3, 2 and 3 are connected to 6, 3 is connected to 7, and 7 is connected to 8. The edges list I have is of length 1, 2, 3, 4, 5, 6, 7. 7 edges. So these are the 7 edges. 1, 2, 3, 4, 5, 6, 7. The first column is the source node. The second column is the destination node. Third column, I added a third column. It's called keep. Whether I'll keep this edge in the final graph or I won't keep that edge. I also added a fourth column. It's called index. It's basically numbering these edges 0, 1, 2, 3, 4, 5, 6. Because what is my logic behind this? It's just because I want to cut this array and I don't want to search for the index again. I want the index to be there from the beginning. Because if I want to set this node to 1, I will just take this index and set keep to 1. I don't want to go to the original array and search. I think this makes it a bit faster, but yeah. So first, let's say the seed node. Let's say the seed node is 1, and from the seed node I will pick 1 edge, and from the neighbor I would pick 2 edges. Just to explain it in the GraphSAGE terminology. So here, k equals the first hop sampled 3 edges. Here I'm sampling 1 in my example, and the second node, the neighbor, sampled 2 edges, and from the neighbor in my example I'm sampling 2 edges. So in my example I'm sampling 1, then I'm sampling 2. So for 1, I pick all the edges that 1 is a source node in that edge. So these are all the edges that where 1 is a source node. And from that array, I would randomly pick one one of these edges. So for example, I picked the node, the edge to 3. Then I would go back to the original edges list and set the edge 1 to 3. I'll set it to 1. I'm going to keep it in the final subgraph. Then the neighbor, I'll pick all the edges where the neighbor is a source node. 3. I'll pick 3, 2, 3, 6, and 3, 7. Then from that array, I would randomly pick 2 of these edges. So for example, I picked 3, 6, and 3, 7. For these edges, I will set 1 and 1 just to keep them in final subgraph. So in my final subgraph would be this one in red. 1 to 3, this was sampled at the first, this was sampled at K1, and 3 to 6 and 3 to 7, this was sampled at K2. All the other edges, all the other edges and nodes, I will just discard them from the subgraph. So before I jump into the neighbor sampler function, I would just introduce you. I would just explain what do I mean by graphs info. So in graph library, they used something called GraphsTuple. The GraphsTuple has number of nodes, how many nodes in the graph, number of edges, how many edges in the graph. The nodes, these are the features of the nodes. The edges are the features of the edges. I'm not using that in my example. And the receivers, it's just a list of integers. It's a list of integers representing the destination nodes. They call the receivers here. And the senders is a list of integers representing the source nodes. But I'm initializing the graphs info. It's an ape tuple. It has the same data type as the graphs tuple, just to keep the train mask for the subgraph, the validation mask, the test mask, and the original labels and the one-hot labels for the source, for the nodes in the subgraph. What I'm trying to do, first I'm creating the train mask for the whole graph. I'm creating the validation mask for the whole graph, the test mask for the whole graph, the labels for the whole graph, and the one-hot label for the whole graph. And based on the nodes that were sampled from the subgraph, I will just sample these lists and just couple them with the GraphsTuple with jraph, just to test the accuracy. So this is my definition for the neighbor sampler. It takes edges, a list of source nodes and destination nodes. It takes the features, the full features for all the nodes in the graph, a train mask for all nodes in the graph, the validation mask, test mask, graph labels, one-hot labels, the seed nodes, a list of the seed nodes that I'm trying to sample from, seed nodes per subgraph, how many seed nodes per subgraph that I'm starting from, and then I'm trying to jump and sample edges and nodes. K1, how many edges are going from the seed nodes. K2 are how many edges are going from the neighbors of the seed nodes. So I'm initializing an empty list for the graph list, and I'm initializing an empty list for the graph info list. The first column is the senders, the second column is the receivers, the third column is a flag whether to keep or remove the edge. That's what I explained in the toy example before. And the fourth column is the index in the original edges list, because from the beginning I want to know their index just for easy access. I don't have to use argware. I don't have to search for them in the whole array. So this is the edges. I'm concatenating zeros just to indicate the keep column for the edges list, and I'm concatenating the edges index for the indices for all edges before I start cutting the array. Just before I go too deep into this function, I would just want to show you an efficient example for implementing a neighbor sampler. This is an example neighbor sample CPU from PyTorch sparse. So this is a C++ implementation of the neighbor sampler. This is what pytorch-geometric samplers are using. If you go to neighbor loader, it calls neighbor sampler. And if you go to neighbor sampler, you would find here the torch sparse.neighbor sample. This basically points you to this C++ implementation. So this is an efficient implementation for the neighbor sampler if you're interested in that. So here I'm shuffling the seed nodes because I don't want consecutive seed nodes in the subgraph, and I'm using the chunks function that I just explained to get the batches. Here for all batch and batches, if the length is less than the nodes in subgraph, I'm basically here I'm discarding the last batch because the last batch has seed nodes less than the seed nodes less than the number that I specified, and I just discarding that graph. For all I in batch, I'm looping over all the seed nodes. I'm getting the edges where the I is the source node. Then I'm just discarding the self loops edges, and I am just and here I'm sampling K1 nodes. K1 is the number that was specified at the input. Then I'm setting these indices into 1. I'm going to keep these edges in the subgraph. Then I'm getting all the destination nodes for the node I, and I'm looping over all these nodes. I'm calling them J. I'm getting all the edges where J is a source node. I'm discarding self loops, and I'm also discarding the edges back to the seed node because I don't want to sample that edge again. I just want to sample going out from the neighbor. Here I'm sampling K2 edges, and I'm setting the keep column for these edges to 1 because I'm going to select these for the subgraph. Here I'm selecting the edges sample, or is all the edges that were their keep column was set to 1. I'm running unique just to assign a new indices for the subgraph. Instead of using the original indices in the full graph, I'm using new indices for the subgraph, and I'm keeping the global indices into a variable called NID. I got the naming from the neighbor loader. So the neighbor loader in pytorch-geometric has NID, which is the global node index for every sampled node. So I'm using the same thing here. I'm assigning new indices for the nodes in the subgraph, and I'm keeping their global indices in a variable called NID. I'm also sampling the feature from the feature matrix. Then I'm setting the edges, the keep column to 0, and I'm looping again over the next batch. If the trail mask is none, this is for the synthetic data, for the toy data that I'll just show you in a second. I'm just packaging the GraphsTuple from jraph. But if it's not none, I'm packaging the GraphsTuple, and I'm packaging the graphs info, the train mask, the validation mask, test mask, the labels, and the one-hot labels. I'm appending the graph to graph list, and I'm appending the graph info into graph info list, and I'm retaining both lists. Now let's check if the neighbor sampler function works as expected. I'm passing the edges from the toy graph, I'm passing the features, and I'm passing none for all the masks. The list of nodes would be from 0 all the way to number of nodes in the feature matrix, and I'm sampling 1 node per subgraph, and from the seed node I'm going for 1 edge, and from the neighbors of the seed node I'm going for 2 edges. So here I'm preparing the plots I'm looping over the graphs and the graph list for all graphs. I'm setting the values of the weights to 1, and I'm setting the columns to the graph senders. I'm setting the rows to the graph senders, and I'm setting the columns to the graph receivers. And the shape of the square matrix will be the nodes.shape0 and nodes.shape0. So it looks like it's working. So this node sends sends an edge to this node, and this node sends 2 edges. So in GCN, this feature vector will be merged into this node, the source node, and in the second layer of the GCN, these 2 nodes will be merged into this node. So yeah, I'm showing a direct edge, but it's not actually direct. It's just the reverse. This is how we sampled. We go from the seed node to the neighbors, then to the neighbors. But in the graph convolution network, basically, we are doing message passing from the neighbors to the nodes itself, to the node itself. So I'm merging their feature vector into my feature vector. So if I change the number of nodes per subgraph, this is basically the same as before, but I change this parameter. I change the seed nodes per subgraph into 2. These are the sampled graphs. So this node here sends an edge here, and this node here sends 2 edges, and this node here sends 1 edge, and this node here sends 2 edges. So I think it's working as expected, except for some cases, and I think there are missing edges, because if the neighbor of the seed node, I'm asking it to sample 2 edges. If it has 1 edge, then it won't be able to sample 2 edges. It will just retain that 1 edge. Yes, and another note in my implementation here, I'm using the GraphSAGE implementation. I'm not using GraphSAINT. And what does that mean? GraphSAGE pick an edge uniformly. So the probability of picking an edge is 1 for all the edges in the graph. So if you go to GraphSAGE paper and you jump all the way here to neighborhood definition, in this work we uniformly sample a fixed size set of neighbors instead of using the full neighbor sets in algorithm 1. So they uniformly sample fixed size. They don't have any preference for what edge to sample. They just set the probability of picking an edge to 1. But in GraphSAINT, they actually use another approach. So to pick an edge according to a probability distribution. So there is a probability to pick an edge. And that probability is defined by this formula. It sets the probability distribution based on the node degree. So the probability of node edge is basically 1 over the degree of the U. U is the source node. I'm using source for source senders, and I'm using destination for the destination receivers. So this is the formula. This is the probability of picking an edge. So if you go to a GraphSAINT paper and you jump all the way to the experiments, yeah, here. This remark here. So one would sample a connection between UL and VL plus 1 with the probability of degree 1 over the degree of u plus 1 over the degree of v. So this is the probability distribution to pick. So in my implementation, I assume that picking an edge is uniformly. So I got 1 for all edges to pick. So there is no preference for picking an edge. No preference according to. You can set the preference using according to the degree, or you can set a preference according if you sample some graphs before. That would be the number of occurrences that the edge was sampled before. But I think that would be very heavy to sample then sample again. Yeah. So this is one important note that I want to explain. So to the experiments, I'm importing the Cora dataset from pytorch-geometric. It has 2,700 nodes, and features is 1,400, and got 10,000 edges. These are some statistics about Cora dataset. 2,000 nodes, 10,000 edges. The average degree is 3.9. The number of training samples is 140, and it's an undirected graph. So I'm putting everything into GraphsTuple. The number of nodes is the first dimension of the feature matrix. The number of edges is second dimension of the edges index. The node feature is the X in the Cora dataset. Senders are the first row of the edges index. Receivers are the second row of the edges index. I'm setting the graph train mask, the graph validation mask, and the graph test mask, and the one-hot labels. Here I'm printing the data type. So it used to be torch tensor, but when I package it into jraph.graphsTuple, I put everything into JAX.numpy. So these are the data types for the senders and receivers and labels. So this is the GCN architecture in graph library. The first GCN layer will apply ReLU to a dense layer here, and second the second GCN layer will just apply a dense layer, and it will retain except applying two GCN layers. Here I'm initializing the GCN to 8 hidden dimensions, and the output dimension will be the number of classes in the Cora dataset, which is 7. I'm initializing the optimizer to be Atom, and I'm initializing the model using the random parameters. Here compute loss will take the predictions on the graph from apply function, and it will compute the softmax for the predictions, and it will compute the loss between the predictions and the one-hot labels. Then the loss masked, it will use the argware just to compute the loss over the nodes in the training mask. I'm not computing the loss on the test mask. So during training, I'm passing the training mask, and during testing, I'm passing the test mask. So this loss and this accuracy are computed according to the mask that was passed here. So for the accuracy, I'm taking the argmax for the predictions along the row dimension, and wherever there's agreement between the prediction label and the ground truth labels, I'm computing the accuracy. So here I'm training on a full batch, and this is a jittable function. So I'm passing the state of the model, I'm passing the graph labels, the one-hot labels at the train mask, and I'm telling the value and grad that the function to calculate the loss is basically this function, compute loss, and it has one auxiliary variable, which is the accuracy. So I'm computing the loss and the accuracy, and I'm also to compute the gradient, and it will apply the gradient using the apply gradient function. So the train step will return the state of the model, the loss, and the accuracy. And I'm training, and I'm calling this train step for the number of epochs, which is I'm setting to 200 here. So I'm passing the train mask, I'm calling the train step, the gradient function, compute loss, and apply gradient. Then I'm going to the next epoch. And for each epoch, I'm printing the step, the train loss, and the train accuracy. Yeah, I'm passing the model state, I'm passing the graph labels, the one-hot labels, train mask, the validation mask, and the number of epochs. And I'm getting a return, I'm getting the train model and the train accuracy. And I'm storing the train accuracy into a list called accuracy list. So at the end, I'm getting, after 200 epochs, I'm getting 100% training accuracy on the full batch training, on the whole graph. And the test is 76%. So here I'm creating many batches using the neighbor sample function I explained earlier. So the neighbor sample function, it was, for Cora dataset, it took 1.5 minutes, which for me was very slow, because in pytorch-geometric it didn't take that long. When I started, it was awful. It was almost 2 minutes, because I was using argware. Argware is a NumPy function that returns the indices of elements that meet a condition, and it has its equivalent in JAX. But when I used it, it was so slow. So I just removed it and add a fourth column to the array just to state the index, because when I just start cutting the array, I want the indices to set the key value to 1. So instead of using argware, I just attached the index for each edge at the beginning, and then I start working on that. So I was able to just reduce the time when I used argware. I think one other thing just to work on is this line of code here, because it's a 1 minute on Cora dataset is a bit slow. So here, I think this line of code consumes so much time. So yeah, the unique indices. Anyways, yeah. So when I pass the Cora dataset into this neighbor sampler, I'm getting a graph list, and I'm looping over these subgraphs. And for each subgraph, I'm printing the graph ID, I'm printing the number of nodes, printing the senders, the number of senders, and the number of receivers. So I got 21 graphs, and on average, I'm training on 1,400, 1,300, so I'm not training on 2,700, which is the full graph, which is all the number of nodes in the Cora dataset. I'm just training on half of that, and I'm not training on 10,000 edges. For each subgraph, I'm having 2,200, 2,500. Yeah, so this was a huge reduction into the graph size. So for the training on mini batches, I need to loop over the all epochs, and also I have to loop over all graphs. So for all epochs in number of epochs, and for all graphs and graphs info in graphs list and graph info list, I'm calling the train step. For the train step, I'm passing the state of the model, the graph, the Y, which is the labels, the true labels, the one-hot labels, and the train mask. And I'm printing, for each epoch, I'm printing the training accuracy, the training loss and the training accuracy. So I'm running for 200 epochs, and at the end, I'm getting accuracy of 93%, which is, let's check the test accuracy. So the test accuracy was 72 on many batches, and 76 on full graph. And this is how it looks. So in full batch, I'm getting 76. In mini batch, I'm getting 72. So yes, this was a neighbor sampler in JAX. It was a very good exercise for me, and I hope you enjoyed it as much as I did. So this code is far away from being efficient. So if you have any suggestions on how to improve the code, on how, on papers that I might have overlooked, please let me know in the comments. All the suggestions and all your feedback is very much appreciated. This was one video on my series in graph neural networks. I was jumping back and forth between PyTorch, geometric, TGL, jraph. So yeah, I think I'll have one more video on this series. Then I'll move. I'll try to get back to vision transformers. So there you have it. By the way, you can find the link to the notebook I'm working on in the description below. Thanks for watching. Bye.